Hello seniors, today we're going to see electronic assignment 16, which is about extrema and optimization problems. The two objectives for today's class are solve optimization problems and solve various application problems. Okay, so the first thing we're going to learn today is something related to a topic that we have already covered, but it's another alternative to find a relative maximum and minimum point of a function. So it says second derivative test. If the first derivative of a function is equal to 0, remember this is the condition in order to find relative minimum or maximum points, right? Then it says, and the second derivative of f exists near that value, then, and this is the rule, if the second derivative is a positive value, it's greater than 0, then the function has a relative minimum at that point at x equals c. If the second derivative is less than 0, that's negative, then the function has a relative maximum at x equals c. And if the second derivative is equal to 0, the second derivative test fails, and the first derivative test must be used to locate the relative extrema. Okay? And pay attention to why this rule makes sense, right? It says, if the second derivative is positive near a value c, which in this case is a minimum, then f is concave up near c. So f has a relative minimum. Pay attention at this graph to the right, and you'll see that this function is concave up throughout the whole interval, right? The function is bending upwards throughout the whole interval. That's why when the second derivative at a specific maximum or minimum point is positive, it means that we're talking about a relative minimum. And the opposite occurs for a maximum point. It says if the second derivative is less than 0 or negative, then f is concave down near c. So f has a relative maximum point at that point, okay? So you see that in this case, when we talk about maximum points, the function is always bending down, right? So it is concave down. So whenever the second derivative is negative for a specific critical number, in this case, this value over here, we're talking about a relative maximum, okay? We're going to see this second derivative test through some examples in order to make this clear, okay? So it says, example 27, find the possible extreme points of each function. Use the second derivative test whether possible. So you see that we're asked to do the same thing we already did during the last classes, right? But now we're using a new method, which may be in sometimes shorter than the previous methods we have learned, okay? So I want to find relative extreme points. That extreme, remember, are maximum or minimum points, right? So let me write this. The word extreme is maximum or minimum points. So we want to find maximum or minimum points of the function, each function. And how? By using the second derivative test whenever possible. So how do we do that? Let's do part A. The first thing we do is we need to copy the function. We need to find the first derivative of the function in order to find the critical numbers, right? So we're going to find f prime of x. And in this case, it's 3x squared minus 6x plus 0, right? So that's it. So then we set this to 0 in order to find critical numbers. This is the same thing we were doing in the previous classes. And then we solve for x. I say you can take a common factor of 3x. We're going to have x minus 2, okay? So one critical value would be x equal 0, which is for this case. And for this case, if we set this to 0, we're going to get another critical number, which is x equals 2. But now we need to determine if x equals 0 corresponds to a maximum or a minimum, and if x equals 2 corresponds to a maximum or a minimum. And how do we do that? And we're going to use the new method we're learning in this class, which is the second derivative criteria. To do that, I'm going to find, first of all, the second derivative of this function. In order to do that, I'm going to find the derivative of this, right? This is 6x minus 6, okay? So, if I evaluate the second derivative with the first critical number we got, which is 0, what do we get? We're going to get 6 times 0 minus 6. And this, as you can see, is a negative number, right? It's negative 6. So we only care about the sign here. So if it's negative, what does the rule say? If the second derivative is negative, then we're talking about a maximum point at x equals 0 in this case, okay? So we can directly conclude, without doing any sign analysis, we can directly conclude that at x equals 0, the function has a relative minimum point, right? And if we can find the y coordinate by substituting the x equals 0 into the original function, right? We're going to get 0 cubed minus 3 times 0 squared minus 2, and this is equal to negative 2. So the point 0, 0 comma negative 2, 0 comma negative 2 is a relative minimum. Okay, so you see that this becomes shorter with the second derivative test. Now, if we do the same thing for our second critical number, x equals 2, we're going to evaluate the second derivative for x equals 2, and this would be 6 times 2 minus 6. This gives us 12 minus 6, which is positive 6. So this is a positive number. And as it is a positive number, according to our rule, whenever the second derivative is a positive number at the value we're evaluating, we're talking about a minimum point. That means that for x equals 2, we have a relative, this should be, say, relative maximum. Maximum, and this should say relative maximum there. So at x equals 2, we have a relative minimum according to our rule. And we need to find the exact point, we're going to evaluate the function at x equals 2. And this would be 2 cubed minus 3 times 2 squared minus 2. And this gives us negative 2. Negative 2, yes. 8 minus 12. Sorry, is it negative 2? No, it's not negative. It's negative 6. Negative 6. That means that the point 2 comma negative 6 corresponds to a relative minimum point. Relative minimum point. Okay, so this would be, let me take this a little bit down. There. So with this method, we can more easily and in a more faster way, we can find a maximum and minimum points. Okay, let's see part B, exercise B. We're doing the same thing. F of x is that, so we want to find relative extreme points, maximum or minimum points. So we're doing the same thing. We're going to find the first derivative first, which is 15x to the 4th power minus 15x squared. We're going to set this to 0 in order to find critical points. This is 15x squared, and here we're going to have x squared minus 1. So one possible value is x equals 0, and the other, we're going to find it by setting x squared minus 1 equal to 0. So x squared is equal to 1. That means that x could be, if we take the square root both sides, we're going to square root x squared, and we're going to get square root of 1. And this is x equals plus or minus 1. So the other two possible values are x equals negative 1 and x equals positive 1. So we have three critical numbers. This one over here, this one over here, and this one over here. Okay, so now we need to see whether each of these critical numbers correspond to a maximum, a minimum, or neither. So to do that, we're going to first find the second derivative to apply the second derivative test, right? Which is the one we're learning today. So we find the derivative of this function, and we're going to get 60x cubed minus 30x. And we're going to evaluate, first of all, with the first critical number, which is x equals 0. So we're going to evaluate the second derivative, f prime prime of 0. And we're going to get as a result 0, right? 60 times 0 cubed minus 30 times 0, that's 0. And if you remember from this, it says if the second derivative is 0, the second derivative test fails. Okay, so we're going to say here that the test fails. So we cannot conclude just by doing this whether for that critical number we're having a maximum or minimum point. And then it says it fails, and the first derivative test must be used to locate relative extrema. So we would have to analyze this from the first derivative perspective, which is what we learned last class. In order to do that, remember, we analyze the signs of the first derivative, and we're gonna draw a number line. We're gonna find 0 here. We're gonna pick a value right before, for example, -1, and right after, for example, 1 or 2 or -2, whatever you want. And we calculate the values, right? F prime, sorry, we cannot choose, now that I see, we cannot choose 1 or -1 because those are critical numbers as well. So I need to change this. Let's pick, for example, -2 and 2. So if we find f prime of -2, we're gonna find this is 15 times -2 to the fourth minus 15 times -2 squared. If we calculate this, you're gonna see that we're getting this is positive, this is also positive. So, and this number is greater than this, so we're getting a positive value. So this is a positive value. We don't care much about the value itself, but rather its sign. So here it is positive. And if we calculate f prime of 2, we're gonna get that this is 15 times 2 to the fourth power minus 15 times 2 squared. And if we calculate this, we're gonna get, this is positive, this is also positive, but this is greater than this, so we're getting a positive value. So once again, this is a positive value, so here we have a positive value. So here you see that actually the critical point x equals 0 corresponds to neither a maximum nor a minimum, because the function is increasing before that point, and then after that point, it keeps on increasing, right? So it's actually an inflection point. It's not a maximum or a minimum, but rather an inflection point. Okay, so I'm going to take all of this a little bit up just to have some space. There. So from this analysis, we can conclude that at x equals 0, we're actually having an inflection point. Okay, so now we need to analyze what's happening with the other two critical numbers, which are -1 and 1, okay? So we're gonna apply our second derivative test, which says that if I evaluate the second derivative for x equals -1, first of all, this would be 60 times -1 cubed minus 30 times -1. And this gives us this is -30. And as it is a negative number, it means that at x equals -1, we're having a relative maximum, right? Remember the rule. If the second derivative is negative, then we're having a relative maximum. Okay, so at x equals -1, we have a relative, let me see if I can make this fit here, maximum. Max, I'm going to write max, a relative maximum point, right? Now, if I find the second derivative for x equals +1, this would be 60 times 1 cubed minus 30 times 1, and this is a positive number. This is +30. And since it is a positive number, we know that that this point corresponds to a relative minimum point. So for x equals positive 1, we get a relative minimum point. Okay? So finally, if we calculate, I don't have enough space here. If we calculate, maybe if I take all of this a little bit up here, there. So if we calculate, let's see, maybe if there's something I'm gonna take this. Move this here. So this is saying that either x is equal to -1 or x is equal to 1. There you go. There. So if we calculate the y coordinates of each of these critical numbers, we will get our final result, right? We already know what each of those critical numbers corresponds to, but now we need to find the respective y coordinates. So f of 0, if we plug in this into the original function, which is this one over here, this is 3 times 0 to the fifth power, minus 5 times 0 cubed. And this is equal to 0. That means that the point 0, 0, according to our analysis, this corresponds to an inflection point. Inflection point. There. Then for f of -1, we're doing the same thing, right? 3 times -1 to the fifth power minus 5 times -1 to the third power, and this is equal to a positive 2. This is, yes, positive 2. Is it? Yes, positive 2. So the point -1, 2 corresponds to a relative maximum point. And finally, for the point f of 1, this is equal to 3 times 1 to the fifth power minus 5 times 1. And this is equal to 3 minus 5, that's -2. So the point 1, -2 corresponds to a relative minimum point. Minimum point. And you see that this makes sense because this point, the y coordinate of this point is above the y coordinate of this point. So it makes sense that this corresponds to a maximum and that this one corresponds to a minimum. Okay? Okay, so I think we're going to leave the class here because then we have another concept which will take some time to do. So this is all for today's class. It's the second derivative test. I hope this was clear for you, people. Remember, these 3 rules are the important ones in order to determine whether a point corresponds to a maximum or minimum point. Okay? So I hope this was clear. If not, please let me know and we will clear it out in future live sessions. See you.